Tonight on The Future of Everything, we've got 3i Atlas updates and maybe even our best shot yet to clearly see the third interstellar object ever detected passing through our solar system. The third ever interstellar object observed from Earth, currently racing through our solar system. Now, astronomers have captured that moment live.
When astronomers first detected Comet 3i Atlas streaking across the depths of space, it immediately stood out as something extraordinary. This was not an ordinary comet bound to the sun's gravity like so many icy travelers before it. It was an interstellar visitor, a cosmic messenger from beyond our solar system, only the third such object ever recorded after the famous Oumuamua and the comet Borisov. But what has recently drawn the attention of scientists and stunned observers at NASA is the comet's astonishing transformation. New measurements reveal that 3i Atlas is expanding at an unprecedented rate, growing in both size and brightness as it approaches the inner regions of the solar system. What began as a distant speck of cold rock and ice has turned into a colossal, glowing phenomenon, defying the expectations of even the most experienced astronomers. Before we start, hit the like and subscribe buttons for more exclusive news. The discovery of 3i Atlas began quietly, as most cosmic detections do. Automated telescopes scanning the heavens for transient objects noticed a faint, fast-moving body traveling along a hyperbolic trajectory, one that would never circle back toward the sun. Its velocity was far too high to be native to the solar system, signaling that it was an interstellar wanderer. Early estimates placed its nucleus at just a few kilometers wide, but within months of observation, the comet's coma, the vast cloud of gas and dust surrounding its icy core, began to expand at a startling pace. The brightness curve climbed far more rapidly than models could predict, suggesting that internal processes were driving an eruption of material from its surface. When NASA's automated sky survey telescopes rechecked its readings, the numbers were clear. 3i Atlas wasn't simply active. It was ballooning into something massive, something never before seen in an interstellar object. Astronomers immediately began recalibrating their instruments to study the outburst. Spectroscopic analyses showed that the comet's outgassing was releasing unfamiliar compounds, molecules not commonly found in comets from our own system. These substances, perhaps born in a distant stellar nursery, hinted at chemical environments vastly different from those that shaped Earth or the Sun. The presence of these exotic ices explained part of the brightness, as their rapid sublimation under solar radiation would produce a spectacular display. But there was more to the story. The expansion rate was too great to be caused by sunlight alone. Some internal mechanism was accelerating the disintegration of the nucleus, creating a cloud hundreds of thousands of kilometers across and growing every week. As telescopes on Earth and in orbit continued to monitor the phenomenon, NASA scientists realized that the comet was shedding mass on a scale rarely observed. The Hubble Space Telescope provided images showing intricate filaments within the coma, streams of dust and vapor radiating outward in spiraling patterns, as if something within the nucleus was bursting periodically, venting gases through fractures in the ice. The resulting plumes gave 3i Atlas a complex, almost floral appearance, with long arcs of light that stretched deep into space. At this point, the comet's visible diameter surpassed that of many known short-period comets, even though its core remained relatively small. The implications were profound. Whatever physical processes were governing 3i Atlas's behavior, they seemed to operate differently from the comets born under our sun's influence. One of the first major shocks came when NASA's Jet Propulsion Laboratory analyzed thermal emissions captured by infrared observatories. The data revealed that 3i Atlas was absorbing and re-radiating energy far more efficiently than expected. Its surface composition appeared unusually dark, perhaps coated with carbon-rich material, but this same property allowed it to heat unevenly, creating intense internal pressure pockets as buried ices vaporized. The expanding gases fractured the crust repeatedly, sending fragments of the nucleus drifting outward. This cyclical explosion-like behavior caused its visible halo to inflate dramatically, as if the comet were breathing, expanding and contracting with solar energy bursts. For planetary scientists, this was a goldmine of information. Each expansion episode offered a chance to study how interstellar material behaves under solar radiation, giving them clues about the building blocks of other star systems. The comet's trajectory itself told another story. Its incoming vector placed its origin somewhere in the outer regions of a neighboring stellar system, possibly flung free after a close encounter with a large planet or stellar body. That meant the materials within 3I Atlas might be billions of years old, preserved from a time before its home star even reached stability. Studying its composition, therefore, was like peering into the deep past of another sun. As NASA scientists compared spectra from 3I Atlas with known comets, they noticed a mixture of familiar and alien compounds, methanol, carbon monoxide, and formaldehyde alongside traces of exotic organics not typically seen in solar comets. The unusual ratio of these compounds suggested that the comet may have formed in an environment rich in volatile ices but low in silicates, possibly near the outer boundary of its birth system's protoplanetary disk. With its ever-growing cloud of material, 3I Atlas became a brilliant spectacle even to amateur astronomers. Observatories around the world turned their instruments toward it, watching as the coma spread out over millions of kilometers. NASA's Solar and Heliospheric Observatory, SOHO, picked up the comet's expanding halo in its wide-field images, showing a faint but growing streak crossing the star-filled backdrop. Every passing day brought a new surprise, an increase in luminosity, a widening tail, a shift in its internal color gradients. The comet was evolving in real time before the eyes of humanity, a dynamic piece of cosmic history unfolding within reach of our telescopes. Perhaps the most startling moment came when radio telescopes detected low-frequency emissions from the comet, signals generated by interactions between its ionized gases and the solar wind. These measurements revealed that 3I Atlas was developing a magnetic envelope of its own, a temporary magnetosphere formed by charged particles streaming off its surface. Such a phenomenon had never been observed at this intensity in any interstellar visitor before. It meant the comet was not merely reflecting sunlight, it was actively interacting with the solar environment in a complex, almost planetary way. The solar wind carved delicate structures into its tail, shaping it into multiple filaments that twisted and shimmered as electromagnetic forces played across them. NASA scientists could hardly believe the data. A visitor from another star system was creating its own miniature magnetic storm inside our solar domain. The expanding scale of 3Y Atlas's coma raised fascinating questions about its potential total mass loss. By measuring the rate at which it was shedding material, researchers estimated that it might completely disintegrate before leaving the solar system. Yet, even if that happened, it would leave behind a trail of dust and molecular debris that could persist for decades, forming a faint interstellar ribbon drifting between the planets. This residue could later be studied by space probes or observed as meteor-like streaks if Earth's orbit ever intersected its path. But beyond the physical traces, 3I Atlas was leaving a scientific legacy far greater, an opportunity to test theories of how interstellar objects evolve under alien conditions and how matter behaves when traveling between stars. While the visual spectacle captured public imagination, the scientific community delved deeper into its implications. 3I Atlas demonstrated that interstellar objects could be far more volatile and unpredictable than previously thought. Unlike Oumuamua, which behaved more like a tumbling rock with minimal outgassing, or Borisov, which resembled an ordinary comet, 3I Atlas seemed to sit between the two extremes, a hybrid, perhaps representing a class of objects that formed in particularly unstable or radiation-rich regions of their birth systems. If that were true, then there could be countless other interstellar bodies wandering through the galaxy, some carrying volatile materials capable of seeding young star systems with organic compounds. This idea rekindled discussions about panspermia, the hypothesis that life's ingredients might spread between stars through comet-like vessels. The growing size of the comet also made it an ideal laboratory for studying the interaction between interstellar matter and solar radiation. As its coma expanded, NASA's Solar Dynamics Observatory captured spectral fluctuations indicating chemical reactions happening in the comet's outer envelope. Ultraviolet radiation from the sun was breaking down molecules, creating new ions and radicals that then recombined in unexpected ways. The reactions produced faint emissions across multiple wavelengths, painting a dynamic picture of chemistry in action. For planetary scientists, this was a rare glimpse into the kind of photochemical processes that might occur around other stars, especially in the early stages of planet formation. As weeks passed, the comet's growth showed no sign of slowing. At one point, its visible halo extended beyond the orbit of the moon if placed in Earth's skies. A staggering comparison that drove home the sheer magnitude of its expansion. NASA's analysis teams noted that the density of the coma remained relatively low despite its vast size, meaning most of it was composed of fine dust and vaporized ice. Yet the optical brightness continued to fluctuate dramatically, indicating that fresh outbursts were still erupting from the core. Each new burst sent waves of particles through the coma, creating rippling brightness patterns that observers likened to cosmic tides. The sheer energy of these eruptions intrigued astrophysicists. Some proposed that the comet's nucleus might contain trapped pockets of gas under significant pressure, remnants of ancient processes that occurred during its formation. As it warmed under sunlight for the first time in perhaps millions of years, these pockets ruptured violently, blowing out jets of material that rapidly expanded. The resulting momentum occasionally altered the comet's spin rate, causing its rotation to become chaotic. NASA's precision tracking instruments recorded tiny deviations in its trajectory, a sign that these internal outbursts were physically pushing the comet around. Such behavior offered a rare window into the mechanical stresses inside icy bodies, helping refine models used to predict cometary breakups. One of the most puzzling observations came from polarization measurements taken by the James Webb Space Telescope. The scattered light from 3I Atlas revealed an unusually high polarization angle, implying that the dust grains within its coma were highly structured, perhaps elongated or coated with complex organic films. This finding stirred excitement because it hinted that the comet's dust might contain prebiotic materials, the same kinds of molecules that could serve as the precursors to life. If such materials were common in interstellar comets, it would strengthen the idea that the ingredients of biology are widespread throughout the galaxy, drifting endlessly until captured by young planets. NASA's Deep Space Network monitored 3I Atlas continuously, coordinating with observatories in Europe and Asia to build a full temporal map of its development. Each dataset added another layer to the mystery. Even as its coma grew colossal, the nucleus remained surprisingly intact, holding together longer than models had anticipated. It was as if some internal cohesion, possibly due to a tough carbonaceous shell, was resisting total fragmentation. This stability under stress offered a clue about how interstellar comets survived their long journeys through space. It also provided insight into why some may endure close stellar encounters without complete destruction. The implications extended beyond cometary science. By studying 3I Atlas, NASA could refine its understanding of how to detect and analyze future interstellar visitors. Each discovery helps improve survey algorithms, making it easier to recognize incoming objects from beyond the solar system before they arrive. The growing frequency of such detections suggests that interstellar visitors may be more common than once believed. Every one of them carries the potential to revolutionize understanding of cosmic chemistry and planetary formation. 3I Atlas, in particular, became a case study for how alien materials behave when exposed to our sun's heat, an experiment nature conducted on a grand, spectacular scale. As the comet continued its journey, NASA scientists used every available instrument to measure its evolving composition. Infrared spectra captured transitions of frozen carbon monoxide, methane, and ammonia sublimating at different rates. By monitoring these emissions, researchers could reconstruct the temperature profile of the comet's surface and interior. The results suggested a multi-layered structure, with pockets of different materials buried beneath one another, like a cosmic time capsule preserving layers of ancient chemistry. Each layer released its gases as it warmed, fueling the explosive growth of the coma. In effect, the comet was peeling away its history, revealing secrets from a time and place far beyond the sun's reach. The dramatic increase in brightness allowed even mid-range telescopes to capture images of remarkable clarity. Astrophotographers produced stunning views showing the comet's broad, fan-shaped tail streaming across the stars. Within it, fine striations hinted at complex interactions between solar wind and dust particles. NASA's magnetometers detected subtle changes in the solar environment near the comet, suggesting that the vast cloud of ionized gas was influencing local plasma conditions. It was an extraordinary thought. A visitor no larger than a mountain was capable of reshaping the electromagnetic field around it on a planetary scale. Even more fascinating were the potential isotopic differences observed in the comet's gases. Spectroscopic readings hinted at unusual ratios of deuterium to hydrogen, indicating that the ices in 3I Atlas formed under much colder conditions than those in the early solar nebula. This reinforced the theory that the comet originated in the outermost regions of its home system, perhaps even beyond the equivalent of its Oort cloud. Such data are priceless to cosmochemists, offering a tangible link to how water and organic molecules might vary across galactic environments. Each ratio, each emission line, is a fingerprint of the environment where the comet was born. The immense growth of the comet's coma also provided an unprecedented opportunity to study light scattering on cosmic dust. NASA's photometric teams analyzed how the comet's brightness changed with angle, learning how tiny particles reflect and absorb light. These studies feed directly into models of how exoplanetary atmospheres and disks might look when observed from afar. In that sense, 3I Atlas became a bridge between comet science and exoplanet research, an unexpected yet invaluable connection between two of the most dynamic frontiers in modern astronomy. The comet's activity also sparked philosophical reflection among scientists. Here was an object that had traveled for eons through interstellar darkness, perhaps ejected from its home system before life even existed on Earth. Now it had come to us, displaying a dazzling show of chemistry and light, a cosmic ambassador revealing the universality of matter. Its growth and transformation symbolized the restless, ever-changing nature of the cosmos itself. Every molecule it released, every shimmer of its tail was a whisper from another corner of the galaxy, a story told in dust and ice instead of words. As 3I Atlas reached its point of maximum brightness, it had become one of the largest visible comae ever recorded for an interstellar object. NASA's astronomers could only marvel at its resilience and volatility. Each image, each data point captured, expanded human understanding of how matter moves between the stars. The comet's colossal halo stood as a glowing monument to cosmic evolution, an object formed around a distant sun, now illuminated by ours, connecting two stellar systems across the void of interstellar space. Even as the days passed and the comet began to drift outward again, its sheer scale remained astonishing. NASA's instruments tracked it with increasing difficulty as it grew fainter, but the legacy of its measurements was already secured. The comet had shown that interstellar objects can behave in ways that defy traditional categories, that the universe is full of surprises waiting to be found in the faintest glimmers of light. The unexpected growth of 3I Atlas, its mysterious chemistry, and its ability to generate magnetic interactions made it one of the most remarkable cosmic events of the decade. As 3I Atlas drifted further into the solar system, its colossal halo of gas and dust continued to evolve, turning the once unassuming object into a sprawling spectacle of cosmic proportions. Its trajectory carried it through regions of solar radiation that intensified its activity even more, and for scientists monitoring it, each passing day seemed to unveil new phenomena. The sheer scale of the comet's transformation turned observation sessions into marathon events. Every image, every data stream revealed some fresh anomaly. Instruments designed to study comets within predictable parameters were being pushed to their limits by an interstellar object that seemed to disregard every known rule of behavior. What NASA's team began to realize was that they were not simply observing a comet. They were witnessing a form of cosmic evolution in real time, an event that would redefine the boundaries of cometary science for decades to come. The deeper the studies went, the more it became clear that 3I Atlas carried secrets about interstellar chemistry that no previous visitor had revealed. Its coma had expanded so vastly that it now resembled a diffuse nebula, its faint edges merging almost imperceptibly with the blackness of space. Within that haze, spectrometers detected a bewildering cocktail of elements, carbon chains of unusual length, nitrogen-bearing compounds, and faint traces of noble gases like xenon and krypton. These gases were difficult to detect even in local comets, and their presence in measurable quantities within 3I Atlas indicated that it had formed under extreme pressure and temperature conditions far different from those of the early solar nebula. Every spectral line told a story of alien origins. To NASA's chemists and astrophysicists, the comet had become a messenger from an ancient stellar nursery, carrying within it the chemical signature of a place humanity could never directly visit. What fascinated the teams most was the distribution of these compounds within the expanding cloud. The gases were not uniform. Instead, they appeared in waves, suggesting layered eruptions over time. This stratification revealed that 3I Atlas was not a homogeneous lump of ice, but a structured body built through countless cycles of accretion and freezing. Some layers might have condensed near the cold outer edges of its native system, while others could have formed closer to its parent star before being buried under newer material. The result was a time capsule spanning different epochs of formation. As solar heat penetrated its crust, each layer was awakened in turn, producing a new burst of activity that fed the comet's unstoppable growth. NASA scientists compared the process to the unrolling of a cosmic scroll, each eruption revealing a fresh chapter of chemical history. Instruments aboard space-based observatories captured something even stranger. The way sunlight refracted through the vast cloud produced interference patterns, like ripples of light bending around invisible structures. This optical behavior hinted at clusters of dust grains forming temporary aggregates before dispersing again. The dust appeared to be electrically charged, influenced by the comet's growing interaction with the solar magnetic field. These microstructures formed and dissolved constantly, creating a shimmering complexity that defied simple modeling. The interplay between dust, plasma, and light turned 3I Atlas into a living laboratory for electromagnetic phenomena, where the laws of physics played out on a visible scale. Each shimmering wave represented the dynamic balance between gravity, solar wind, and electrostatic forces, a natural dance billions of kilometers from home. Astronomers tracking the object's brightness noted peculiar periodicities, small oscillations in luminosity that suggested the comet might be spinning unevenly. The erratic rotation could have resulted from repeated jets of vaporized material acting like miniature thrusters, altering its spin rate unpredictably. This chaotic motion likely caused stress fractures to propagate through the nucleus, releasing even more gas and dust. Observations from NASA's Near-Earth Object Wide Field Infrared Survey Explorer confirmed this hypothesis, detecting short bursts of thermal activity aligned with the suspected rotation period. The nucleus was behaving almost like a pressure cooker, trapped energy building beneath the surface until it vented explosively into space. The dynamics of such violent ejections offered clues about how fragile interstellar bodies survive the long voyage between stars. Most objects ejected from their home systems are believed to be destroyed over eons by cosmic radiation or micrometeorite impacts. Yet 3I Atlas had endured, carrying its volatile contents intact across light years of emptiness. That endurance implied either a protective outer crust or a composition that allowed the body to self-heal through refreezing vapors in deep space. NASA's modelers began constructing simulations that treated the comet's surface as a porous, sintered layer of mixed ices and carbon compounds, a natural armor against the cold void. This composition might also explain why the comet had resisted complete fragmentation even after multiple violent outbursts. While ground-based observatories focused on optical and infrared data, radio telescopes recorded the frequencies emitted by charged particles streaming from the comet's surface. The ionized tail produced a faint but detectable radio hum, a byproduct of interactions between solar particles and cometary plasma. These emissions fluctuated in intensity depending on the comet's orientation and solar wind strength. The rhythmic pulsing reminded some researchers of auroral processes seen on planetary magnetospheres, though on a far smaller scale. The idea that an interstellar comet could generate radio emissions visible from Earth was astonishing, suggesting that the object possessed intrinsic magnetic characteristics shaped by its original environment. For NASA's heliophysicists, this presented an unprecedented opportunity to study how extraterrestrial magnetic fields behave when exposed to solar influence. Meanwhile, NASA's analytical teams continued refining measurements of the comet's expansion. By integrating optical and infrared observations, they determined that the coma's diameter was increasing at a rate of thousands of kilometers per hour. At certain points, it grew so large that it spanned an area comparable to that of a small planet's orbit. This meant that photons from the sun were interacting with an immense surface area of gas and dust, producing a complex web of radiation pressure effects. The solar wind was not merely pushing on the comet's tail, it was sculpting its entire morphology, stretching it into intricate streamers that undulated like fabric in a cosmic breeze. The modeling of these processes required supercomputing resources, as no previous comet had displayed this combination of scale and dynamism. The implications extended into planetary science as well. By studying how solar wind shaped 3I, Atlas's tail, scientists gained insights into how protoplanetary disks may have evolved around young stars billions of years ago. The same fundamental forces, light pressure, magnetic fields, and particle flows, would have influenced dust and gas in those ancient systems, driving them toward the formation of planets. In this way, the comet's activity served as a miniature reenactment of processes that built entire worlds. Each jet of vapor and stream of dust was a living echo of the cosmic forces that once sculpted solar systems. Back on Earth, the images of 3I Atlas began to dominate scientific publications and news outlets. The comet's expanding glow and unpredictable surges captured the public imagination in a way few space events had done since the great comets of the past. Artists' renderings depicted it as a vast emerald or sapphire mist stretching across the heavens, a visual metaphor for the unknown wonders drifting through interstellar space. For NASA scientists, however, it represented something even more profound, a chance to test the limits of human understanding against nature's unrestrained creativity. One of the most fascinating challenges came in explaining why the comet continued to grow long after the models predicted it should have exhausted its volatile reserves. Typically, once a comet's near-surface ices sublimate, activity decreases as deeper layers take longer to heat. Yet 3I Atlas defied this pattern, maintaining high levels of outgassing even as it receded from the sun. Infrared observations suggested that its interior might contain supervolatile materials, substances capable of vaporizing at much lower temperatures than water ice. These could include carbon monoxide or nitrogen ices, which, if trapped beneath a crust, might sustain activity long after solar energy waned. This endurance turned 3I Atlas into a cosmic paradox, a dying object that refused to fade. At the same time, the comet's immense size allowed it to interact with the solar wind in ways usually reserved for planets or large asteroids. Its magnetic tail stretched millions of kilometers behind it, occasionally forming knots and twists that reflected shifts in solar output. Each solar flare that erupted from the sun sent shock waves through the comet's plasma environment, generating visible waves of light and color within its structure. It was as if the sun and the comet were locked in a silent dialogue, a stellar wind meeting an ancient traveler, exchanging energy across space. NASA's monitoring satellites captured these exchanges in exquisite detail, producing data that would later help refine understanding of solar system magnetohydrodynamics. The human fascination with interstellar comets lies partly in their rarity and partly in their symbolism. They are the physical manifestations of the connection between star systems, the proof that material can migrate across cosmic distances. 3. Atlas embodied that truth on an unprecedented scale. Its enormous growth symbolized the richness of interstellar chemistry, the capacity for matter to evolve, expand, and transform under new conditions. To many scientists, it felt as though the universe itself had sent a message, a vivid demonstration that creation and destruction are inseparable forces woven into the very fabric of existence. Among the most startling findings during the observation campaign were the unusual color shifts within the coma. Normally, cometary halos exhibit a predictable gradient from white to pale blue due to sunlight scattering on fine ice particles. But 3I Atlas displayed streaks of deep green, crimson, and violet that changed over time. These hues corresponded to emissions from molecules excited by ultraviolet radiation, but the variety and intensity suggested complex interactions involving organic compounds. When NASA's spectrometers isolated the responsible emissions, they found evidence of polycyclic aromatic hydrocarbons, large carbon-based molecules often considered precursors to life. This discovery electrified the scientific community. It meant that materials capable of forming biological structures could exist abundantly in interstellar space, carried within icy travelers like 3I Atlas. The potential implications reached far beyond comet science. If such organic-rich objects are common in the galaxy, they might serve as natural delivery systems for life's ingredients. The idea that amino acids and hydrocarbons could journey across the stars aboard frozen messengers gives new weight to theories about the cosmic origin of life. It suggests that Earth's own biological beginnings might be part of a universal pattern rather than an isolated event. 3I Atlas, in this sense, was not just a visitor. It was a bridge between systems, a carrier of cosmic heritage. Another dimension of its study involved tracking the polarization of sunlight scattered through its coma. These observations revealed subtle asymmetries that implied the presence of unusually shaped dust grains, possibly needle-like or fractal in geometry. Such complex structures would greatly enhance light scattering, explaining the comet's intense brightness. More intriguingly, the fractal nature of these grains hinted that they had formed under conditions of slow aggregation and low turbulence, environments typical of distant cold regions of space where density gradients are gentle. This reinforced the notion that the comet's origins lay far from any star's warming influence. The dust of 3I Atlas was ancient, untouched and unaltered since the dawn of its parent system. NASA's modeling teams took these observations and began constructing three-dimensional simulations of the comet's structure. The models depicted a nucleus riddled with pockets and channels through which gases escaped, feeding the massive outer envelope. When compared to known solar comets, the differences were striking. Whereas local comets often showed discrete jets, 3I Atlas's activity seemed more diffuse, as if entire sections of its surface were venting simultaneously. This widespread activity suggested that the internal structure was not compact but spongy, an airy matrix of ice and dust with a porosity far exceeding typical expectations. Such a configuration would allow heat to penetrate deeply and release trapped gases from multiple layers at once, fueling the unstoppable expansion. The study of such porosity also carried broader implications for astrophysics. It provided clues about how planetesimals, the building blocks of planets, might form in protoplanetary disks. If objects like 3I Atlas can maintain integrity despite extreme porosity, it suggests that early planetary formation may involve fluffier, less dense materials than previously assumed. This, in turn, affects theories of accretion and collision dynamics, reshaping the understanding of how solid bodies grow in young systems. As the comet continued to evolve, its influence extended beyond scientific research. The spectacular images coming from NASA's observatories inspired renewed public interest in space exploration. 3I Atlas became a cultural phenomenon, symbolizing humanity's curiosity and insignificance in the face of the cosmos. For many people around the world, gazing at the comet through telescopes or following NASA's updates provided a profound sense of connection to something larger than themselves. It was a reminder that even across light years, the universe finds ways to touch our skies. For NASA engineers and mission planners, 3I Atlas represented more than inspiration. It was a target for future exploration concepts. Proposals began circulating for missions that could intercept future interstellar objects, capturing in situ data before they moved beyond reach. The comet's unpredictable growth and volatility underscored the need for agile, fast-response spacecraft capable of launching within months of detection. The challenge was immense, but the rewards were equally vast. Direct sampling of alien material untouched since the dawn of another solar system. 3I Atlas had effectively opened a new frontier in planetary science, one that extended beyond the boundaries of the sun's domain. Meanwhile, data continued to flow in from telescopes around the world. Every measurement reinforced the sense that the comet was rewriting the rules of cometary physics. One particularly baffling observation involved the temperature gradient across its coma. Thermal maps indicated that some regions of the halo were significantly hotter than others, by hundreds of degrees. These thermal anomalies could not be explained solely by solar heating, suggesting that chemical reactions within the gas cloud were generating additional energy. NASA's chemists theorized that photolysis, light-driven breakdown of complex molecules, was producing radicals that recombined energetically, releasing heat in localized bursts. This process would make the comet not just a passive reflector of sunlight, but an active participant in its own transformation, a self-heating engine powered by its chemistry. As months passed, 3I Atlas began moving farther from the sun, but instead of fading quickly as expected, it maintained a surprising level of activity. Its residual glow lingered, sustained by internal heat and chemical processes. Even as its trajectory carried it toward the outer planets, telescopes continued to pick up emissions from its vast envelope. The comet seemed reluctant to surrender its radiance, as though determined to make its presence known before vanishing into interstellar night once more. This persistence offered further clues about its internal composition. Some of its ices were likely undergoing phase transitions that released latent energy slowly, acting like a fading ember rather than a sudden flare. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on 3I Atlas growing so unexpectedly huge? We want to hear from you. Thank you for watching, and see you next time.